Imagine trying to build a machine that has to um, survive being plunged into an actual blast furnace and then immediately thrown into a deep freeze.
Oh, and don't forget being constantly bombarded by invisible radiation, too.
Right, all while operating in an absolute vacuum. When you think about just the sheer hostility of outer space, it's honestly a miracle that human beings have managed to put anything up there at all.
Let alone highly sensitive equipment that, actually functions. I mean, it really is the ultimate engineering crucible.
Yeah, there's no roadside assistance in space.
Exactly. The margin for error is effectively zero. You can't just pull over to the side of the road and pop the hood if a valve sticks or if a computer glitches in the middle of a vacuum.
And that is exactly why we are doing a deep dive into this today. We're looking at a massive, comprehensive Wikipedia breakdown of the history, the classifications, and just mechanics of spacecraft.
A lot of material to cover.
It is, yeah. But our mission is to cut through all that dense aerospace jargon and really figure out how humanity actually builds these survival boxes.
Because when you strip away all the acronyms, the story of spacecraft is really the story of how we outsmart environments that actively want to destroy us.
Which is wild. So if we look at the historical data, understanding that survival really starts with defining what space actually is. Because, Earth doesn't just end with a hard border.
Right. The atmosphere just gradually thins out. It's a gradient. So the aerospace community basically had to draw a line in the sand, or, well, a line in the sky, I guess.
Okay, let's unpack this.
Yeah.
Where is the official starting line for spacecraft?
So the internationally recognized boundary is called the Kármán line.
The Kármán line, okay.
Yeah, and it sits at an altitude of 100 kilometers, which is about 62 miles above sea level.
So why 100 kilometers? Is that just a nice round number they picked?
It's actually not arbitrary at all. At 100 kilometers, the atmosphere becomes so incredibly thin that if an airplane, wanted to generate enough aerodynamic lift to stay aloft, it would have to fly at orbital velocity anyway.
Oh, wow. Which means wings basically become useless.
Precisely. Wings do nothing up there. So to cross that boundary and officially become a spacecraft, you have to abandon aerodynamics and rely entirely on brute force thrust.
Right.
And unless you're dealing with a theoretical single-stage-to-orbit vehicle, you need a massive launch vehicle to get there.
Wait, single stage to orbit? I feel like I see that term thrown around in sci-fi movies all the time, but what does it actually mean in practice?
Well, it's kind of the holy grail of aerospace engineering. It means a ship that can just take off from a runway or a pad, fly all the way to orbit, and return without shedding any fuel tanks or booster rockets along the way.
Just one solid ship the whole time.
Exactly. But the reason it's largely theoretical comes down to the rocket equation.
The math ruins it.
Always does.
Yeah.
To go fast enough to reach orbit, you need a tremendous amount of fuel. But fuel is incredibly heavy.
Right, so you need more thrust to lift the fuel.
Which requires even more fuel. It's the vicious cycle. So the most efficient solution we've found is staging. You drop the heavy empty fuel tanks as you climb, so you aren't wasting energy carrying dead weight into orbit.
Which makes total sense.
Yeah.
And what's just wild to me is that the first machine to actually cross that 100-kilometer boundary, shedding its weight and hitting space, wasn't doing it for science.
No, not at all.
It was the German V2 rocket back in 1944. It reached an altitude of 189 kilometers, which is a really sobering origin for such an incredible technology.
Yeah, the roots of spaceflight are undeniably tied to warfare. But the true dawn of the space age, the moment orbital mechanics shifted from theory to reality, that happened on October 4th, 1957.
Sputnik 1, launched by the Soviet Union. And I feel like Sputnik gets kind of a bad rap in popular culture today.
How so?
Well, people usually just picture this, like polished metal ball with 4 antennas aimlessly beeping as it tumbled around the Earth. But reading through these sources for our deep dive, I realized it was so much more than a beeping sphere. I started thinking of it as this cosmic weather balloon.
That's a great analogy. What stands out to you about its design?
Honestly, the ingenuity of its simplicity. It wasn't just a passive object. It actively measured atmospheric density just by how its orbit decayed over time.
Right. The drag on the sphere told them how thick the thermosphere was.
Yes. But the coolest part, it was filled with pressurized nitrogen. It functioned as a giant orbital sensor.
Oh, the micrometeoroid detection.
Exactly. If a micrometeoroid punctured the hull, the nitrogen pressure would drop, the internal temperature would change, and the pitch of the radio signal it beamed back to Earth would actually alter. So it was physically reacting to the environment.
That mechanism is a perfect example of elegant engineering. I mean, Sputnik was a total paradigm shift. It traveled at 29,000 kilometers per hour.
That is just incomprehensible speed.
Right. Completing an orbit every 96.2 minutes. It forced the entire world to literally look up and realize that the ultimate high ground had just been occupied.
And that realization just triggers this massive leap in ambition. Because if you can put a pressurized metal ball in orbit and keep its internal environment stable, the immediate temptation is to stick a person inside it.
Of course it is.
But doing that completely fractures spacecraft design into two totally different philosophies, right? Crewed and uncrewed.
Yeah, and what's fascinating here is how severely biological logistics penalize spacecraft engineering.
The meat sack problem.
A meat sack problem, exactly. The moment you decide to put a human on board, the complexity, the weight, and the cost of the mission just increase exponentially.
Because humans are incredibly high maintenance.
Yeah.
I mean, we're essentially soft bags of water that require constant pressure, oxygen, temperature control, food, and waste management.
Yeah, we're very needy. And beyond that, we're massive contamination hazards.
Oh, right. The microbes.
Exactly. Humans are basically walking ecosystems covered in billions of microbes. So if you're sending a spacecraft to a pristine environment, say, searching for microscopic life in the ice of Jupiter's moon Europa, a human crew is a disaster waiting to happen.
Right. You contaminate the very thing you're trying to study.
Exactly. And you cannot put a human being inside an autoclave to sterilize them.
Yeah. Please don't try to bake your astronauts. I feel like that's a bad idea.
It generally ends poorly for the mission, yes. But a robotic probe, you can bake those components at extreme temperatures, blast them with radiation, and ensure they are totally biologically inert before they even leave Earth.
Wow. Okay. So that is why our robotic spacecraft are sent to the most vulnerable, pristine, and frankly, hostile environments in the solar system.
Exactly.
But I want to dig into how those robotic explorers actually operate. Because, when we send a probe out to Jupiter or Venus, is someone just sitting at a desk at NASA with a joystick, treating it like a glorified remote-controlled car? Or does the spacecraft have a mind of its own?
Well, the laws of physics basically dictate the answer to that. It all comes down to the speed of light limit.
Okay.
If probe is attempting a complex maneuver at Jupiter, it takes radio signals anywhere from 35 to 50 minutes just to travel across the solar system to Earth.
Oh, wow. So if a camera spots, like a cliff face during a landing sequence?
By the time that image reaches Earth and a human operator says, "Oh no," and sends the command to fire the thrusters and steer away, the probe has already been a smoking crater for over an hour.
That is terrifying.
Right. So out of pure necessity, these machines possess varying levels of autonomy. They execute incredibly complex pre-programmed algorithms. They have to read their sensors, process the data, and make life or death mission decisions completely without us holding their hands.
Here's where it gets really interesting, though, because that requirement for absolute autonomy is pushed to its absolute limit when you look at the spacecraft that have essentially cheated the physical boundaries of our solar system.
You're talking about the Voyager probes.
Yes, launched way back in 1977.
The Voyager program represents an absolute pinnacle of trajectory planning.
Yeah, I was reading about the launch vehicles for Voyager 1 and 2. They used Titan Guy rockets. But those rockets didn't actually have enough thrust to send a 722-kilogram probe all the way to Saturn, let alone completely out of the solar system.
No, not even close.
So they had to steal energy using gravity assists. And I've always kind of struggled to visualize this. How does a tiny metal box steal momentum from a gas giant without just crashing into it?
Think of it like a ping pong ball bouncing off the front of a speeding freight train.
Okay, I'm picturing it.
The train is moving toward you at high speed. When you throw the ping pong ball at the train, the ball bounces back much, much faster than you threw it. The ball essentially steals a minuscule fraction of the train's forward momentum.
Oh, I see.
So in space, the planet is the freight train, and its massive gravity well is the bumper. The probe falls into the gravity well, swings around the planet, and uses the planet's orbital momentum around the sun to fling itself outward at a substantially higher speed.
So wait, the planet actually slows down.
Technically, yes. Jupiter loses an infinitesimally small amount of its orbital energy to speed up the Voyager probe.
That is incredible.
It is a brilliant theft of physics. But to pull it off, NASA had to take advantage of a planetary alignment of Jupiter, Saturn, Uranus, and Neptune that literally only occurs once every 175 years.
The logistics of coordinating that just completely blow my mind, especially the launch timing, because I noticed Voyager 1 actually launched 16 days after Voyager 2. I had to read that twice to make sure it wasn't a typo.
Yeah, it wasn't a typo. Voyager 1 was placed on a faster, much more direct trajectory to Jupiter, whereas Voyager 2 took a longer, more winding route, specifically so it could catch the necessary alignments to visit Uranus and Neptune after Saturn.
That's just wild. And today, Voyager 1 is the farthest human-made object in existence. It's over 160 astronomical units away from the sun.
Well, it's a staggering distance.
Right, and for context for you listening, 1 AU is the distance from the Earth to the sun. So Voyager 1 is 160 times farther away from the sun than you are right now.
It really is hard to wrap your head around. But these deep space probes face a pretty grim reality regarding power.
Because they're so far from the sun.
Exactly. They cannot use solar panels because the sunlight out there is incredibly weak. Instead, they rely on RTGS radioisotope thermoelectric generators.
Which are basically nuclear batteries, right?
Essentially, yes. They harness the heat generated by the natural decay of a radioactive isotope, which is usually plutonium-238. Then they use thermocouples to convert that heat directly into electricity.
Okay, but as the plutonium decays over decades...
The heat output drops.
Good.
Exactly. NASA is constantly playing a game of triage right now, shutting down scientific instruments one by one just to keep the transmitters warm.
That's so sad.
Sometime after 2036, the RTGs will no longer generate enough power to run the communications suite. The probes will just drop out of range of the Deep Space Network and go completely silent.
Just a one-way trip into the dark. It is deeply poetic. But, that expendable one-way philosophy only really works for deep space. Closer to home, in low Earth orbit, throwing away millions of dollars of hardware after one use is a massive problem.
It's completely unsustainable.
Right. If you want to put humans into orbit regularly, you have to bring the ships back. And falling from orbit isn't like flying a plane down. It's literally like dropping into a blast furnace.
Because the atmosphere creates immense friction and compression heating when a vehicle re-enters at those orbital velocities.
And for decades, the standard answer to that heat was the capsule. Vehicles like Vostok, Soyuz, or the Apollo command modules, they're these blunt, simple shapes. They fall through the atmosphere and they survive using an ablative heat shield.
Yes, the ablative shielding.
I've heard the term ablation before, but what is physically happening to the bottom of that spacecraft during re-entry?
So ablation is basically a process of intentional, controlled destruction. Yeah. The heat shield is made of specialized materials, often carbon composites or resins, that are designed to absorb immense amounts of thermal energy. And as they heat up, the material literally vaporizes.
It just boils off.
Exactly. It changes state from a solid directly into a gas. This phase change absorbs heat, and as the gas expands and blows away from the spacecraft, it carries all that blistering heat away with it, which prevents it from melting the crew cabin.
So the ship survives by literally burning away its own armor.
That's one way to put it, yeah.
But because those capsules often land in the ocean or take a heavy beating on the ground, they are incredibly hard to reuse. Which brings us to the great pivot in the 1980s, space planes. Specifically, the Space Shuttle.
Ah, the Space Shuttle.
It was pitched as this reusable space truck that would fly like a commercial airliner. But looking at the sources, it really didn't, did it?
No, it didn't.
Yeah.
If we connect this to the bigger picture of aerospace economics, the Space Shuttle highlights the paradox of reusability. Well, it was an undeniable technological marvel. I mean, it flew 135 times. It could lift 29 tons into low Earth orbit. It carried the Canadarm, which practically built the International Space Station, but it completely failed its primary economic mandate.
Because it wasn't actually cheap.
Yeah.
If the entire goal was to make spaceflight cheap and routine through reusability, why did NASA approve a design covered in thousands of fragile, custom-shaped silica tiles? I was reading that you could literally dent the shuttle's heat shield tiles with your fingernail.
Yeah, they were extremely delicate.
That seems fundamentally backward for a vehicle meant to take a beating and fly again.
It was a compromise, really, born out of the materials science available at the time. To avoid the heavy, blunt force ablation of capsules, the shuttle used a thermal protection system meant to radiate heat away while keeping the aluminum airframe underneath cool.
Okay, so insulation rather than ablation.
Exactly. And those silica tiles were incredibly efficient insulators. You could heat one side of a tile to 2,900 degrees Fahrenheit and pick it up by the corners with your bare hands just a few seconds later.
That's crazy.
It is. But the trade-off for that thermal insulation was extreme structural fragility.
Which created a logistical nightmare upon landing.
Exactly the problem. After every single flight, teams had to meticulously inspect thousands of individual tiles. And if one was damaged, it couldn't just be swapped with a generic spare.
Why not?
Because each tile was uniquely machined for a specific contour of the orbiter. Plus, the solid rocket boosters had to be fished out of the ocean, taken apart, and rebuilt.
Oh, wow.
The absolute fastest turnaround time they ever achieved between landing and relaunch was 54 days, and that was with the Space Shuttle Atlantis.
That isn't refueling an airliner. That is rebuilding a bespoke prototypes after every flight. The labor costs just ate any savings from reusability.
Exactly.
Which brings us to how companies are trying to solve that paradox today. Because SpaceX's Starship is attempting to be fully, rapidly reusable, both the booster and the ship itself.
Right. Starship relies on a stainless steel architecture and tougher, more uniform hexagonal heat shield tiles, aiming for that actual airline-like operational cadence.
But to achieve that massive payload capacity while carrying the weight of a reusable heat shield and landing fuel, it introduces a new, massive logistical hurdle.
Orbital refueling.
Orbital refueling.
Right, because to get to Mars, Starship burns almost all of its fuel just escaping Earth's gravity well. So it just parks in low Earth orbit with empty tanks.
This is the brutal math of the rocket equation once again. Elon Musk has estimated it might take around 8 separate launches of specialized tanker starships just to ferry enough liquid methane and oxygen up to low Earth orbit to refuel one outbound Starship.
8 launches just for one deep space mission. It just proves how stubbornly strong Earth's gravity really is. But, whether you're talking about a massive Starship, a fragile space shuttle, or a tiny Voyager probe, every single one of these machines has to survive the exact same environment.
That's true.
They all rely on the same anatomy of survival under the hood.
Yeah. Every spacecraft, regardless of its mission profile, is built around a core set of critical subsystems.
Right.
Without them, the vehicle is literally just expensive dead weight. I actually found it really helpful to think of these subsystems in biological terms. It kind of grounds the abstract engineering. For example, you have astronautics, that's the electronic brains and the nervous system of the ship, the computers processing the telemetry.
Right.
Then you have GNC, guidance, navigation, and control. This is the inner ear and the spatial awareness.
And GNC is critical because there is no up or down in a vacuum.
Good point.
The spacecraft uses star trackers, which are basically cameras that map constellations and gyroscopes to constantly calculate its orientation. Then it fires tiny thrusters to point its antennas at Earth or its cameras at a target.
Then you have the power system, which is essentially the metabolism, solar panels if you're near the sun, or those nuclear RTGs if you're out by Jupiter. But the subsystem that absolutely blew my mind the most was thermal control.
Oh, thermal control is fascinating.
Because outer space is notoriously cold, but it's actually an environment of extremes.
Yeah, thermal shock is one of the fastest ways to destroy a spacecraft. If a satellite is in direct, unfiltered sunlight, the exposed metal can heat up to hundreds of degrees. But the moment it passes into the shadow of the Earth, that temperature drops instantly to hundreds of degrees below zero.
So you basically have to give the ship the mechanical ability to sweat and shiver. I get how a ship shivers. You install electrical heaters along the fuel lines so the propellants don't freeze solid in the dark. But how does a ship sweat?
What do you mean?
Well, there's no air in space. You can't use a fan to blow hot air away from the computers. How do you physically cool down in a vacuum?
Ah, right. You cannot rely on convection, which requires a fluid like air or water. You have to rely entirely on thermal radiation.
Okay, how does that work?
Spacecraft use active fluid loops. They often pump ammonia through the hottest parts of the ship, like the avionics bays or the crew cabin.
Oh, ammonia.
Yeah, the ammonia absorbs the heat and is pumped out to massive radiator panels on the exterior of the ship. Those panels then emit that thermal energy out into the void of space as infrared light.
That is just incredible. The ship cools itself by literally glowing in invisible light.
Exactly, and they use mechanical louvers, which are essentially metallic blinds, that open to expose the radiators when the ship is running hot and then close to insulate the ship when it passes into the freezing shadow.
And it is wild to think that all of this, the GNC mapping the stars, the ammonia loops radiating infrared heat, the nuclear batteries, it is all just life support for the payload.
The payload is the whole point.
Right. The payload is the telescope mirror, the communications dish, or the human crew.
In the aerospace industry, the payload is what pays the bills. But if any one of those unglamorous, highly engineered subsystems fails, that billion-dollar payload is instantly frozen, fried, or just lost in the dark.
But when all those systems hum together perfectly, you get machines that push the very limits of what physics allows. We talked about Voyager 1 being the farthest, but I was looking at the speed records. The Parker Solar Probe is currently the fastest human-made object in history.
It is, yeah. It's utilizing repeated gravity assist from Venus to gradually shrink its orbit, diving closer and closer into the sun's corona.
It is currently traveling at over 343,000 kilometers per hour. And at its final close approach, its perihelion, it is estimated to reach 700,000 kilometers per hour.
Mind-boggling numbers.
Right. To put that in perspective for you listening, at that speed, you could travel from New York to Tokyo in under a minute.
And it survives that proximity to the sun using an incredibly advanced carbon composite heat shield, managing thermal loads that would vaporize most metals.
It's terrifying speed, but honestly, my favorite machine from these sources isn't setting speed records. It's doing the quiet, everyday heroics of orbital logistics. Let's talk about the Mission Extension Vehicle, or MEV, built by Northrop Grumman. This is essentially a robotic tow truck for dead satellites.
It is a brilliant application of autonomous GNC technology. Satellites in geostationary orbit, orbiting at the exact speed the Earth turns, so they stay parked over one spot. They often outlive their fuel supply.
So they run out of gas before they break down.
Exactly. Their communications electronics work perfectly, but without thruster fuel, they cannot maintain their precise position. And a drifting satellite is a useless satellite.
So rather than letting a perfectly good multi-million-dollar satellite become space junk, the MEV launches, autonomously navigates to the dying satellite like it did with Intelsat 901 back in 2020, and it physically docks with it.
Yes, it physically grabs hold.
The MEG then fires its own thrusters, essentially taking over as the satellite's new engine. It corrects the orbit, gives the dead satellite another 5 years of life, and when it's done, it just tows it to a safe graveyard orbit out of the way.
It proves that orbit is no longer just a place where we passively leave things. It is a dynamic, highly active ecosystem that we are finally learning to manage.
So what does this all mean? Well, it connects directly back to you, going about your day. The invisible infrastructure of your modern life, the communication satellites routing your internet, bouncing your television signals, synchronizing global financial transactions. That infrastructure isn't just floating passively up there.
Not at all.
It is actively sweating, shivering, and being rescued in a chaotic environment by robotic tow trucks.
The journey from our first attempts to where we are now is just staggering.
We started with the V2 rocket, making a brief, violent, 189-kilometer hop into the dark. And from there, we figured out ablation, gravity assists, and ammonia cooling loops.
We built pressurized biological habitats.
We attempted reusable spaceplanes, engineered autonomous tow trucks, and launched nuclear-powered probes that are currently coasting 160 times farther from the sun than we are right now.
It is the ultimate testament to the human drive to extend our reach. But, looking at all this, specifically comparing the mission expansion vehicles fixing old satellites with the inevitable power failure of the Voyager probes, it raises a very interesting question for you to ponder.
Oh, where are we going with this?
Well, we know Voyager 1 and 2 are drifting, and they will go permanently dark in the next decade or so. But propulsion technology never stops advancing. It inevitably gets faster and more efficient.
Okay, yeah.
So will a future spacecraft, perhaps hundreds of years from now, launch with an advanced drive, catch up to Voyager 1 in the deep void, and perform a mission extension on it?
Oh, wow.
Or will we one day retrieve our furthest explorer, not to reactivate it as a scientific probe, but to salvage it, bring it home, and place it in a museum as a silent relic, the ultimate symbol of our very first steps into the dark?
Wow. A rescue mission for a 50-year-old battery.
Wow.
I love that thought experiment. Thank you all for joining us on this deep dive. Keep looking up, keep asking questions, and we'll see you next time.